Hi, I'm Alyssa. This is work I did at the Vrije Universiteit in Amsterdam. I now work for Whisker, a security lab. I do trusted execution, and I work on a lot of embedded applications, which is also quite practical for this work. And I'm going to talk about uninitialized data. So what is it? Because what does uninitialized mean? Because surely when your computer boots, you're going to get your memory zeroed, your kernel is going to be handing you zeroed memory. This is kind of crazy. So what we're talking about here is reuse of memory, which happens all of the time in current applications. So I'm just going to go through a quick example. We're going to say here we allocate some memory. Let's say we're a web server, and we put some secret encryption keys in it, maybe the private keys. And then at some point we say, OK, we've done some pre-processing on these keys. We're done. And we free the memory. And that means that the value is gone, right? But of course it isn't, because all of these secret keys are still in memory somewhere. So let's say an attacker connects to our web server, and we allocate a buffer. And that buffer happens to be placed at exactly the same place in memory where our secret data was. And then if the attacker finds something like an error path, which is actually quite a common vulnerability, and this memory doesn't get initialized, then what happens? We send our secret data over the network. And this is just the information exposure kind of vulnerability. It's the first one that comes to mind. There's also another important type of data which gets leaked, which is metadata, in particular pointers, which are really critical, as we just discussed, for ASLR, for protecting against ASLR. But there's also two other important types of vulnerabilities I'd like to talk about. One of which is what happens if you use that uninitialized data. You can influence the control flow. And in fact, there have been vulnerabilities where attackers make use of uninitialized function pointers, which is a quite critical level of problem. But also, another problem is if the compiler optimizations manage to work out that this data is never going to be initialized, then they say, aha, this is undefined behavior. And they will do horrible things to your code and remove things like error checks that you thought were sure to be there and protecting you against attackers. And is this a real problem? Because we have compiler warnings. They say, hey, this is uninitialized. And for a start, this only happens in the front end of compilers, but you also have static analysis tools. A more critical problem is that programmers don't care. This is just one search of GitHub for one warning flag that turns this stuff off, but even if you have warnings turned on, people ignore the warnings. So what are we actually trying to solve here? Can we look at some examples? So for example, we can consider QEMU, which is used to run code which you might not trust. In fact, you might be running a whole virtual machine provided by an attacker. So you have vulnerabilities such as this one, which is leaking stack memory. How do you fix this? You simply patch it to initialize the memory that you weren't initializing before. And if we look at another vulnerability, same type of thing, it also gets fixed in much the same ways. We just initialize the memory. So if we just initialize all of the local variables and all of the members of structures, is this enough? It's not, because we have another problem, which is struct padding. You have structures like this. You have a char, which is 1 byte at the start of your structure. But then you have an integer as your next member, and the compiler wants your structure to be aligned for performance reasons, and so you get this space in between. What happens if you initialize every member of this struct? Does that mean all your memory is initialized? Of course not, because you have, for example, these 3 bytes. And if you had, say, a pointer in your memory before that, you've just given up pretty much all of your ASLR entropy. If you go and copy this, for example, over the network into user space from a kernel into guest space. Speaking of user space, another example is Linux. And this is another example of a vulnerability, and this one involved struct padding. How do you fix it? We initialize the memory. Now, if you go and look at more and more of these patches, you start to think, wait a minute, what is shared in common between all of these patches? Just can we not do something automatically? And of course we can. What are these patches doing? They're setting everything to 0. They're just initializing all of the memory. So what if we just zero all the things? What if we just initialize absolutely everything? So this is the system that we built. It's called SafeInit, and it literally just initializes everything. It's that simple. So we want to initialize all of the heap memory. Some allocators already do this, but we also want to initialize the stack memory, in particular all of the local variables. So one important thing, we do want to initialize all of the local variables, even if these allocations are overlapping in the frames. So we can't just initialize the entire frame at startup. Helpfully, initializing the whole frame at startup turns out to be really, really slow as well. We did this using a custom allocator, but also a compiler pass, which initializes all of these local variables as they're used. And you're going to say, OK, but programmers are kind of lazy. I mean, we already saw they ignore all the warnings. So this sounds like an awful lot of work if they're going to have to do any work here. So we implemented it in the compiler. It's literally just an extra flag, and it magically fixes your vulnerabilities. So we built this, as you can probably guess, on top of Clang and LLVM. And we also made use of a modified version of tcmalloc. It's a high-performance heap allocator. So the thing is, isn't this really, really slow? We're going to initialize all of this memory. That's kind of crazy, right? So I'm saying I want to zero all of this memory. And in fact, what SafeInit literally does is, to make sure nothing goes wrong, it really makes sure everything gets zeroed in the compiler pass. So the trick is, if we look at an example, OK, we have a local variable here, and it's obviously very clearly initialized. We set it to 1. And of course, what's actually happening is we're reserving some stack memory, and then we're setting that stack memory to a value. But I want to zero all of the things, so I add a 0 in here. And it's like, OK, doesn't this lead to an additional store that's completely unnecessary? But of course, one of the very first things your compiler optimization chain does is it says, OK, wait a minute. This store, there's another store beforehand that we can get rid of, and so we kill the earlier store. We also, importantly, do get rid of undefined behavior problems here. Because if we take another example where we're doing something that is uninitialized, so we're just printing a literally uninitialized local variable, this is a bit unexpected to some people, what happens in the compiler. So if we look at LLVM, we look at the very first pass, which runs in the optimization chain. This is kind of like LLVM IR, but basically what we're doing, we allocate some stack space, we load a value from that stack space, and then we pass it to printf. And the first thing that runs in LLVM's optimization pass is something that tries working out, OK, can we predict the value that will be loaded? And it says, of course we can predict this value. This is undefined behavior, undef. And it then quickly optimizes this into this. It's just passing undef to printf. Now, if you come along later in the optimization chain, or if you run something like valgrind later, is it going to catch this? You've just thrown away any information you might have had about this being a local variable because the constant's been propagated all the way into the function call. So one of the most important things is we run very first thing in the optimization pass chain. So this is what happens, again, this is going back to the start, what happens if we just zero all of the memory. We literally just use LLVM's memset intrinsic in our prototype. We just set the entire thing to 0. We get all the padding this way. And what happens then, isn't this completely unnecessary? But of course, compilers are smart. It says, OK, if you load a value from this memory, that value is 0. And so we pass 0 to printf. And this is the result you get. And it's like, OK, this kind of sucks. We were really hopeful that these magical compilable optimizations, we just start initializing everything, it should remove everything, right? The problem, of course, is that the compiler optimizations in modern compilers, they don't want to do unnecessary things. And it turns out that in real-world code, this is not that common a pattern where you initialize chunks of memory and then you stomp over it again afterwards. It's something which definitely gives you performance improvements, but also gives you compile time regressions. So how are we going to fix this? Well, it turns out that we actually have to do more work than just inserting some memsets. We have to actually develop some optimizations to prove that you can do this. But we're really trying to keep this to something you can practically implement in a compiler. And what you don't want is to build something that uses a lot of overcomplicated static analysis that is not going to work in the real world, because my real world are these people who just turn off the warnings because they don't want to see them. So the very first thing we do is we make sure that we push the initialization to the last possible moment where we know the memory in question is going to get used. So if we have an example here, we have some local variables, which we're not going to care about. But later in the function, we have an error path. And it has this huge buffer, which is used for some kind of error message. This is a pretty common pattern. And the obvious thing to do is at the start of the function, we just clear all of the local variables. This is a very bad idea because it means every time you initialize this buff, every time you call the function, this buff is going to get initialized. In the real world, this buffer doesn't actually ever get used because we never reach this path. What we want to do is only initialize it if we actually reach this point. And this in itself brings a substantial performance improvement. Obviously, this is still not enough. So we have various other optimizations. I'm not going to describe them in detail in a 15-minute talk. We added write-only buffer detection. And again, kind of the power of this approach is that it's things which the compiler authors are going to do anyway. And this write-only attribute for annotating buffers as write-only, which is to say scratch memory, this happens enough in real programs that it's actually an upstream attribute now in LLVM, although I don't think it does all of the work we did at the time, because of course this is from May last year we were doing this work. We also took rejected patches for dead storm elimination, so eliminating unnecessary stores. Again, they were actually backed out of mainline LLVM because they led to compile time regressions and actually also slowing down code itself. We patched them up. We also added new functionality. We made them support non-constant lengths. So if you initialize the first n bytes, where n is a runtime only value, then it works for that. We also support initializing with non-constant values. For instance, if you have a loop that initializes with an integer value of 1, happens a lot, you can't turn that into a mem set, and typically compilers only look at this. And we also introduced a bunch of other optimizations. For example, often we can work out string buffers are safe. If you copy a null-terminated string into a buffer, and then you copy a null-terminated string out of a buffer, then we know we don't have to initialize the memory beyond the null terminator. So does this actually fix the problem? Do we get a decent performance overhead? We go back to look at SPEC, at CINT. I will say if you want the floating point numbers, they're similar. They're in the paper. And my text has failed. Drat. OK, this should have a nice little bar showing the average overhead is 3.5% now. It's not great. It's actually ruined by this Sheng bar, which actually goes up to, I think, 36% or so. But the other benchmarks have really had the unnecessary uninitialization mostly removed. It's not great. You can fix this code dramatically by just changing a few little things in the source code or adding, I think, one annotation to Sheng. But it's acceptable performance. But OK, who cares about SPEC? What about the real world? What about web servers? So these are real worst-case numbers for nginx. If you run it over a 1 gigabit interface and you just start serving files, you turn off logging, you turn on pipelining, you make it as bad as I possibly could, you don't get any overhead because it's really not CPU bound and you don't notice the latency. This is over the loopback interface. It's as bad as you can make it. So instead of using the system calls, which are on the right side, we actually copy buffers around manually. And it turns out the compiler pass SafeInit doesn't know about system calls. And so it does do some unnecessary initialization there. But even then, we keep the overhead below 5%. And the last thing is, we tried it on Linux. And this is micro-benchmarking system calls. This is also not very realistic. If you have a no-op system call, then you get no overhead, great. But it does turn out that in the very worst case, this is the worst case figures. You can see the nice figures in the paper. Then if you do fstat, it ends up initializing things in the file system layer that it shouldn't be. And in the very worst case, if you keep on doing protection faults, then it's 6%. But again, this is naive. This is only on the stack because we don't know, because the pass is automatic. It doesn't know about the kernel heap. There was some work presented at CCS last year on called Unisan, which adds some static and which does some static analysis to avoid information exposure from the kernel, and you could combine it with this work to produce something even better. And of course, the most important thing is, does this actually work? Does this actually mitigate anything? And the answer is yes. Often it's really easy to tell. You just compile it unoptimized to start with and make sure that beforehand you take a test case, which is often supplied with vulnerability, and you make sure Valgrind complains. Afterwards, you make sure Valgrind doesn't complain. Obviously, if you optimize the code, Valgrind often stops complaining because the compiler has just removed all of this code and you don't know what the heck it's doing. We also manually checked some CVEs. I should know it's often really difficult to check this because the assembly code often changes drastically because just making this minor change of initializing it makes all of the other steps of optimizations very different. So this is the question. Often you end up with performance improvements in micro benchmarks just because the compiler happens to do something different. So in summary, SafeInit just mitigates this whole class of vulnerabilities by just guaranteeing initialization everywhere. We attained acceptable overhead in almost every circumstance except if you're constantly doing protection faults. And the Linux, please don't do this. But it also gets even better as compiler optimizations improve because most of the work here is really in the compiler optimizations. The source code's on GitHub. I'd love to see it upstreamed. If anyone would like to talk to me about that or really about any of this, then please come and talk to me. And of course, see the paper for more results. So thank you very much.